Now let's just move on further towards the new topic, which is nothing but called as the angle which is subtended by an arc of a circle. So rather than the chord, we are just now talking about the angle which is subtended by an arc. So let us suppose if I'm just talking about the two end points of a chord other than the diameter of the circle, then we definitely know that the two ends of the chord always form two types of an arc, which is nothing but a major arc and a minor arc. So for an instance, if I'm just talking about the two equal chords, then what can we say about the size of the arcs that are formed by the two equal chords? So let us suppose if I'm just talking about these two equal chords, then what can we say about the size of the arcs that are formed by these two equal chords? So which actually leads us toward a very special important result, and the result says that if we have the two chords of a circle that are equal to each other, then their corresponding arcs are congruent to each other, and converse statement is also true. Means if two arcs are congruent to each other, then their corresponding chords are also equal. So this is a very special important result which is all related with the two chords, that is nothing but AP and CD, which are equal in length with each other. Then they do have the corresponding arcs being congruent to each other as well. Now for an instance, if I'm just moving on further and I'm just talking about the angle which is subtended by an arc. So the angle which is subtended by an arc is actually as taken as the angle subtended by the chord. So if we just have the two congruent arcs, then what can we say about their angles? So we can say that the congruent arcs or the equal arcs of the circle, they subtend equal angles at the center. So this is again a special result which is all related with the congruent arcs and the angle which is formed by them at the center of the circle, that they are always equal to each other. So these two important results are actually leading us towards a special theorem, which is nothing but a theorem which says that the angles which is subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. So now we have to prove that the angle which is subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. So if we are just talking about the angle which is subtended by an arc, so the arc can be of three type. It can be a major arc, it can be a semicircle itself, and it can be a major arc. So for the three cases, we are going to prove this particular theorem. So let us suppose if I'm just forming up the circles over here for the major, minor and the semicircle. So let us suppose these are the three figures that I'm taking up over here. So first of all, you can see that over here I'm taking PQ as nothing but a minor arc. In the second case, I'm taking PQ as nothing but an arc, which is nothing but a semicircle. You can see all by yourself that this PQ, if I'm joining this PQ, this is actually passing through the center of the circle. And furthermore, if I'm just talking about this PQ, so this is nothing but a major arc. So I'm actually just taking the three cases and I will prove this particular theorem for all these three cases. Now let us suppose if I'm just starting with the given condition, that what is given to us? Given is nothing but a circle. Given is a circle with the center O, and an arc PQ subtending an angle POQ at the center of the circle. So since the arc, this leads us towards three cases. What are those? First of all, the arc PQ is a minor arc. Second, arc PQ is a semicircle. third arc PQ is a major arc. So we are just taking the three cases over here, that arc PQ is a minor arc, arc PQ is a semicircle, arc PQ is a major arc, and we are also taking A being any particular point on the remaining part of the circle, and A being and we have any point and A being any point on the remaining circle. Now let's just start with the construction which is related with it. So first of all, if I'm just talking about the construction, so the construction would be like join AO and extend it to B. So as you can see over here, if we have the construction as AO, so this is my A and this is my O, and you can see a B already over here. So I'm actually just joining this AO and extending it to B, in such a way. Again, this is my A for this case, again this is my O for this case, and I'm joining this OA together, extending it to the B. Now furthermore, again, if I'm just talking about this A, I'm further talking about this O, so I'm extending it towards B, just like this. Now again, you can see that if I'm just talking about this particular angle, and if I'm just talking about this particular angle, or if I'm just talking about this particular angle, so they are actually the exterior angle of the triangle OAQ, and again OAQ. In all the three cases, let us suppose if I'm just considering as the case number 1, this is the case number 2, and this is the case number 3rd. This is the case number 3rd, and now we can see that. Let us suppose if I'm just talking about to prove what we need to prove over here, we need to prove that the angle POQ is actually double the angle of PAQ. In all the three cases, we just need to prove this thing. Now let's just start with the proof. So what can we say over here? We can say that since angle BOQ is the exterior angle of the triangle OAQ, then angle BOQ is equal to the angle OAQ plus the angle OQA. Why so? Because of the reason that exterior angle is equal to the sum of interior opposite angles, is equal to the sum of interior opposite angles. So using that concept, I can just say that BOQ is actually nothing but is equal to the sum of OAQ plus OQA. Let us suppose if I'm putting it under a box and I'm calling it as nothing but the equation number 1. Now furthermore, we can say that in the triangle OAQ, OA is equal to OQ being the radii of the circle, and since if they are the radii of the circle, then we can say that the angles which are formed by these two equal sides would be equal. OAQ should be is equal to OQA. Why so? Angles opposite to equal sides are equal. So we already know about this thing, and hence using this particular thing, let us suppose if I'm calling it as 2, so substitute 2 in 1, we can say that angle BOQ is actually is equal to angle OAQ POQ plus angle OAQ, which is twice of angle OAQ. It is twice of angle OAQ, which implies the angle BOQ is twice of the angle OAQ. So actually what we are getting up over here, that the angle which was the exterior angle for the triangle OAQ, means this angle is actually coming up as twice of this particular angle. It is coming up as twice of this particular angle. So similarly, in the same way, we can talk about this particular angle which do exist as an exterior angle for the triangle OAP. So in the similar sense, this angle would also comes out to be equal to the double of this particular angle as well. So what we can say over here, similarly the angle BOP should be equal to the twice of the angle OAP. Similarly, we can say this thing. Let us suppose if I am calling it as 4. So add 3, add 4. What we are getting at the end? Angle BOQ plus angle BOP is equal to twice of angle OAQ plus twice of angle OAP. So this would be nothing but a total angle BOQ, BOP plus BOQ. BOP plus BOQ is nothing but the total angle, this which is nothing but POQ. And furthermore, OAQ plus OAP is actually nothing but the total angle, which is nothing but this angle, that is PAQ. So hence this is POQ, which is equal to the twice of the angle, which is PAQ. As you can see all by yourself that they are forming the whole complete angle, which is nothing but of this form. And this is exactly what we need to prove, that POQ is actually nothing but is equal to twice of PAQ. So this is actually for these two cases. But since we are talking about the third case as well, so we can see over here that this PQ is actually forming up a major arc over here. Since it is forming a major arc, so we are talking about the reflex angle over here. So this is similar for the case 1 and case 2. So we can say for case 3, reflex angle POQ should be twice of the angle PAQ. For the case 3, this should be nothing but a reflex angle that we have to take. This should be nothing but a reflex angle that we have to take. So for the case number 3, reflex angle POQ should be equal to the twice of the angle PAQ, and this is exactly what we need to prove over here. So this is nothing but a theorem which says that the angles which is subtended by an arc at the center is actually double the angle which is subtended by it at any particular point on the remaining part of the circle.